Hello, fellow problem solvers. So they're going to be doing a problem from a competition. I don't know which one this is, but it says, let pk be the largest prime divisor of k. Prove that for infinitely many integers n, positive integers n here, we have pn minus 1 is less than pn is less than pn plus 1. Right, I'm going to invite you to try this number theory problem out for a minimum of 20 minutes, ideally an hour, but not more than 2 hours. If on the other hand you'd like to go along with us, put your first set of ideas out on paper for the next 5 to 10 minutes. And now without further ado, let's begin. So what do we have here? We have that this sort of condition, okay, we need to show that this holds true for infinitely many n. Prove that something holds true infinitely many times. Assume it doesn't. It holds a constant number of times. What does that mean? It means that after some n, we will always have that this isn't true. Like for every small n greater than this big N, which is a constant, like it can be a huge constant, we will have that this is never true. Right, so, okay, what happens then? Well, this is not true either because Pn was less than Pn minus 1, or because Pn was greater than Pn plus 1, right? It's because of one of these two reasons. Okay, well, this thing will not always be true, right? And if this thing isn't true, this other thing needs to be true. We'll need to have that. Okay. So if, say, what happens here? If Pn is greater than Pn minus 1, then this implies that Pn needs to also be greater than Pn plus 1, right? For any such n. So that's what we have on one hand. And on the other hand, we have ever that Pn is greater than, is actually less than Pn plus 1. Then Pn is also less than Pn minus 1, right? So we have these sort of like two ifs. Okay? What is best for us to use here? Is there anything else that we know about this sort of function? Like this Pn, what is this relationship to, say, pk? Well, we know it's the largest prime divisor of k, so p of a times b is the bigger one of p of a and p of b, right? We have this multiplicative sort of rule, and we don't have an additive rule that I think is simple. We might have a non-simple additive rule, but this is the best sort of, we have a multiplicative rule. Let's see if we can use it somehow. And here's where I invite you to pause for the next 5-10 minutes and see if you can use this multiplicative rule and this fact that this, so you suppose the contrary in these sorts of problems, and can we use this here? That if this is true, then this needs to be true. Does this lead us to a contradiction in some way, shape, or form? And now's the time to pause and do that. And here's sort of the next step. So we have, when we look at p of n squared, we have p of n squared is equal to p of n. And this is equal to the maximum. P of n squared minus 1 is equal to the max of p of n minus 1 and p of n plus 1. Right? And why is this cool? Because now we know we have one thing for p of n with its relationship to these two, and that gives us a relationship for the next one, right? So here, what would that mean? Well, if say the second case happened, if p of n was less than p of n plus 1, then p of n would also be less than p of n minus 1, and we would get that so then we would get that this thing right here is going to be less than the max here. So we'd get this is true. And this is again this case. Is it this case? No, it's not. Actually, we would not get anywhere, right? We wouldn't get something. So let's look at the other case. Let's look at if this is true. And the reason we don't get anything is because this sort of relationship holds true for the smaller one. So actually, we want to now look at this case. If p of n is greater than this, and then this implies it's greater than this, we have that, and this needs to hold true. Like this doesn't need to hold, this hold true then, right? So Given this, I invite you to pause for another 10 to 15 minutes and try to push the problem further. Because here's the next step. Now we have this. Okay, so p of n squared is greater than p of n squared minus 1, right? And now, by the same rule, this implies that p of n squared needs to be greater than p of n squared plus 1, right? So we have another thing. And now we will get what? We will get that this needs to hold true. If it holds true once, and it certainly does, right? You can have p of n minus 1 be 2 to the power of alpha for a huge alpha, and then the p of 2 to the power of alpha is 2. And then this is going to be odd, so it's going to be bigger than 2. And so we can have this hold true. So once it holds true once, it seems this thing will hold true right now for everything else. Right now we can have n to the fourth is greater than n to the, p of n to the fourth is greater than p of n to the fourth minus 1. And that implies p n to the fourth is also greater than p to the n to the fourth plus 1. And now, but n to the fourth, n to the eighth, n to the 2 to the power of alpha, all of these are equal to p of n. And now we have this. We have p of n is greater than p of n to the power of 2 alpha plus 1 for all alpha. Right? This is what then holds true. This is the conclusion. Now, this number becomes incredibly large. And we're saying that the largest prime divisor is bigger than this fixed thing. This just doesn't, how do I say, add up, right? So, given that this does not add up, can we prove that it doesn't add up? And here's where I invite you to take this pause for now, 5 to 15 minutes and see if you can prove that. And here's what you need. You need to show, like, wait, can p of n to the power of 2 alpha plus 1 and p of n to the power of 2 to the power of beta plus 1, can these two numbers be identical, right? Can these two things be the same? And the answer is no. Why not? Well, say alpha is greater than beta, and then we have p of n to the power of 2 alpha minus 1 is going to be equal to the maximum of, because this n to the power of 2 alpha minus 1 is n to the power of 2 to the alpha minus 1 times n to the power of 2 to the alpha minus 1 plus 1. And then we can, do the factoring there again, like we're really just doing x squared minus 1 is equal to x minus 1 times x plus 1. So we'll have this whole thing, because this whole function is multiplicative, is going to be the maximum of n to the power of 2 to the alpha minus 1 plus 1 and, plus 1 n to the power of p of n to the power of 2 alpha minus 2 plus 1, and it's going to cover p to the power of 2 to the beta, p to the power of n to the power of 2 to the beta, everything plus 1, all the way till n squared plus 1 and p of n plus 1, right? So this about covers it. This means that, what does this tell us? It tells us that this thing right here is going to have the prime divisor, which divides p of. It's not that it'll have the prime divisor which divides it, but it means that if these two things were identical, then we would have p divides n to the 2 alpha minus 1, p divides n to the 2 beta, actually n to the 2 alpha plus 1, but then because it divides this, it also would divide p to the power of n to the power of, p would divide n to the power of 2 to the alpha minus 1, and then we'd have p needs to divide 2. All right, this highest prime power would need to be 2. However, let's just make n to be, what can we make n be if n is even? this will then not be able to happen. Actually, not n. Yeah, if n is even, this will never happen, right? We can have n be like p of n, like the initial n be 2 times a prime, and then that's bigger than 2p plus 1 and 2p minus 1. Or potentially not. Actually, it will be bigger than one of the two. Can we find consecutive primes? I think we can now find a number here. It starts once. Oh, wait a second. No. Can this be? Then this is 2, but 2 will not be the. No, but then this won't be 2 forever. Like this cannot be 2 that many times. Can it be 2t alpha? Yeah, there's a way to finish this out. Like this is really not the hard part. Let me think about it, okay? And here's sort of the end of my thoughts. Let me sort of clear this up. So I just figured out like, wait, let me just put n minus 1 to be 3 to the power of alpha. Like the only thing I need is this initial thing to hold true for an even n, and then I won't have this 2 problem. So because then n is even, this will hold true infinitely many times, because if this only doesn't hold true if this is 2 to the power of some x, but 2 to the power of x minus 1 equaling 3 to the power of y only has a handful of solutions, namely only x equals what? X equals 1, y equals 0, x equals 2, y equals 1. And the way we prove this is by using modules, namely, if you assume x to be greater than, say, 3, you can just use like modulo, what do I need? I need to say so by modulo, if I assume y to be greater than 2, I'll use greater than or equal to 1 actually, I'll just use modulo 3 to get that 2 to the x, which is minus 1 to the x. It needs to be congruent to minus 1 modulo 3, which means that 2 divides x is equal to 2 sum t, 2t, and then this is 2 to the x, 2 to the t minus 1, 2 to the t plus 1 is 3 to the y. This is 3. Now, if both of these were divisible by 3, then their difference, which is 2, would be divisible by 3. That is not the case. So this is 1, and this is 3 to the power of y. And now you get the equation that when you subtract these, you have 3 to the power of y minus 1 is equal to 2, which forces y to be equal to 1. And so this will not happen at all. When you set n minus 1 to be 3 to the alpha for some huge alpha, you'll get the initial n, which is even. Beautiful. And then this doesn't happen. And now we get a contradiction because this p of n is bounded, but this sort of thing right here is, we're saying like it's a constant, but this sort of thing is not bounded because p of n to the alpha plus 1 is never equal to p of n to the power of 2 beta, n to the power of 2 to the power of beta plus 1. Like these two things are never equal. It's a mouthful. And this finishes up our problem. And like the reason it finishes it up is because then this sort of thing, if you just have call the sequence of p of n to the 2k, for k is 1 through infinity. These will all be different, but and which means they aren't bounded by any constant because they're prime numbers. Yeah, I think because they're prime numbers, they're not bounded by any constant, and so we're done. This cannot hold true for every single one of them. This finishes up our problem, and as always, thanks for problem solving.